Hello again, welcome back to the lectures. Today we have lecture 11, and in continuation to what we have been doing in the previous lecture, I will show you some of the examples that are made using physical vapor deposition, and we will try to understand what are the capabilities and certain aspects of physical vapor deposition itself. And then we will look into the chemical vapor deposition and also familiarize some examples out of that. And then I will also introduce to you something called moire pattern. I think it is better we discuss that when you see that for the first time. It is a different and interesting pattern that you normally observe solid interfaces. Well, that is also observed in daily life. You will see basically the examples. And now let us look at the examples from physical vapor deposition. So, in the previous class we have discussed how to do the physical vapor deposition, and I have actually convinced you that in the physical vapor deposition the best methods are actually the electron beam evaporation and also the normal thermal evaporation methodologies, because with that we can precisely control atomic layers, and you can even control at atomic precision. That is the important fact here. And this is extremely important because if you want to make an interface and you want to apply in technology, you want to also have high reliability of the technology itself. And then of course, if you are actually just messing at the interface, you are actually just going to have a bad working device. Therefore, it is extremely important that we actually end up in an atomically precise interfaces. And as we go actually down with the feature size, that today you can actually hear that the transistor size are actually going down to below 10 nanometer. Yeah? When you want to have a transistor which is below 10 nanometer, it is extremely important to have atomic level precision for the interfaces that you actually make in creating a transistor. Yeah? We have already seen transistors are actually just created by different type of interfaces, and if the transistor itself is extremely small, then the atomic level precision is very important. And that is actually the reason why this kind of physical vapor deposition, or you will also see the chemical vapor deposition in general, are extremely important in developing thin films and heterostructures which is directly applied in technology. Now let us take a few examples and we try to understand a few aspects of it. Now what I am showing you is actually a germanium deposited on silicon 100 surface. Now you see something interesting is happening. Now we are actually just getting close to real examples. Silicon 100 surface. Now by now you all know how a silicon 100 surface looks like. It is a 4-fold symmetric surface. Now germanium, when you deposit on silicon 100 surface, so these are actually nothing but STM images. What you are seeing here in A, B, C, D are actually some kind of a coverage dependent images. So you have here the blue area is nothing but silicon. So this is basically the silicon surface itself, and what you are seeing here in this green and orange color is nothing but the different layers that are deposited of germanium on silicon surface. Now interesting thing is, as you increase the coverage, or that means as you increase the amount of atoms that are actually bombarding on the silicon surface, you can basically see the amount of germanium that is actually getting deposited on the surface increases. That is no big deal, that is very good. But now something interesting you mark here, that the islands are actually forming like a rectangular islands. Each islands, if you look, the islands are basically looking like different shapes, but they are all different type of rectangles that you are forming on the surface. What is that? You can actually think about that while you are listening the lecture. We will come back to that in a minute. And you see, like as the coverage increases, the different type of rectangles are forming, and now rectangles are also forming in two different directions. So they are also forming like this, or maybe another, this one is actually getting extended and so on. So the rectangles are actually forming in one direction like this, another direction like this. Now of course the height is also increasing. You can basically see the height of the islands are increasing. It is not just a monolayer of germanium, on top of silicon, it is actually many layers of germanium is actually getting deposited on top of the silicon surface. Now, let us look at another interesting example. It is actually sodium chloride. So, the examples I am showing here is actually to make you familiarize with the variety of materials that you can actually deposit. Here you have salt. The question is, can you really deposit salt? Of course, we can deposit. We need to use the electron beam evaporator, because to evaporate sodium chloride you would need a lot of temperature. So, if you can actually achieve that temperature, you can easily evaporate sodium chloride, for example. Now, look at this, you have basically sodium chloride on gold 111 surface. So, that is the surface. You know what is a 111 surface. Gold is of course an FCC type of packing, it is a 111 surface, and again what you are seeing is actually the STM images. Now, at low resolution, what you are seeing here is actually, if you carefully look in the images, you can basically see that herringbone type of reconstruction, that is just showing you that is a gold surface, and on top of that you basically see islands that are looking more or less like square and rectangular shape, or you can say with a rectangular or square facets. Yeah, we will come back to that in a minute. And if you zoom into that, you can basically see the atomic resolution. That is what I said, STM is always good for resolving atomic level structures, and this is basically the edge of the island, and you can see now within the islands you can see atoms are basically arranged in a square manner. Yeah, so that is nothing but the sodium chloride atoms. Now, you can also take a cross sectional profile along this white dashed line that is given here, and that is a cross sectional profile which is given here. And now, from the cross sectional profile you can also basically calculate how many layers of sodium chloride is basically getting deposited. You can already see that here in the beginning I have only 3 layers, and then this is actually another step edge of gold, therefore I also have about 3 layers of gold. So, this is what it is, and just keep thinking about why is it looking more or less like a square or a rectangular facet at which the sodium chloride is growing. We can look at one more, now you may actually understand. So, I have another material that is deposited, cobalt on top of copper 111 surface. Yeah. So, copper 111 surface, it is also something you know it, we have already discussed in the previous class, that now I am depositing basically cobalt on top of copper 111 surface. Now, the interesting thing, if you look here, the islands here are looking more or less like a triangle, yeah, or triangle of this shape or a triangle of this shape. That is interesting, right? And in fact, if you look at more carefully, you would even find that this angle that these triangles are forming are just 60 degrees. That is also interesting. Yeah. Now, the question here is basically what is actually controlling, or why do we see this different type of islands, or why do we see this particular shape of the islands itself. Now, look back into the symmetry of the silicon 100 surface. Yeah. As we would recollect, the silicon 100 surface is basically a 4-fold symmetric surface. Well, a 4-fold symmetric surface, if I would basically deposit atoms on top of a 4-fold symmetric surface, if this would be the way the atoms are arranged on the silicon surface, let us imagine that this is basically the silicon. Now, we take a different color for the germanium atom, and now imagine the germanium's atoms are basically getting deposited like this. What do you see? You see basically a rectangular or a square type of island on top of the surface, right. So, now as the germanium atoms grows on top, so this is germanium. So, if I would basically just deposit the germanium on top of silicon, so silicon 100 surface, that is extremely important. On the silicon 100 surface, the symmetry of the surface basically defines how the germanium should grow, and that is the reason why we see these kind of rectangular and square type of islands on top of that. That means it is completely influenced by the symmetry of the surface itself. Now, when it comes to the sodium chloride on gold 111, so that is something much more interesting. In that case, you would recollect immediately that the gold 111 surface is actually a 6-fold surface. Yeah? Gold 111 surface is actually a 6-fold surface. It has a 6-fold symmetry. But now when you look at the sodium chloride itself, what you suddenly see, the island of sodium chloride, what you suddenly see is that the surface itself is basically some kind of a square or rectangular in shape. What is the reason for that? Now comes the interesting aspect to consider here. When an adsorbate go onto the surface, there are two major interactions. We will look in detail in the next class when it comes to the energetics. When an atom goes onto the surface, there is a strong interaction, like we have already discussed, that is the interaction of the atom onto the surface. Now when there are two atoms next to each other, two adsorbate atoms next to each other, they also start to interact. That is actually known as the adsorbate interaction. Now there is a competition always between the adsorbate interaction and the adsorbate surface interaction, and that finally decides what is actually the shape of the island that you form. So it is very clear in the case of sodium chloride on gold 111 surface that the interaction between the sodium and the chlorine atom is so strong that actually the gold symmetry is actually not observed in the final island that is formed. That is quite spectacular, which is also something you might have intuitively thought, because sodium chloride is known to be a very strongly interacting, or it is actually a strong solid. That means the sodium is always ionically interacting together with the chlorine and forming the strong sodium chloride itself. So that means it is no matter what is the symmetry of the underlying surface, for materials which are having a strong adsorbate interaction, everything is going to be controlled basically by the adsorbate interaction. But in the case of germanium on silicon, there is also a strong germanium silicon interaction, because both are semiconductor, they both strongly interact to each other. Therefore, the silicon germanium interaction is actually very strong at the interface, and therefore it actually grows on the same way. At the same time, the symmetry is also maintained of the surface. That is the reason why you see that the germanium islands are looking rectangular and the sodium chloride islands are looking also rectangular in shape. Now when it comes to the cobalt, the copper 111 surface is basically 6-fold symmetric, and that is exactly what you are seeing in the angle of the island. So if this would be basically the different orientations of the copper lattice, and all the different copper lattices will be basically rotated also by 60 degree. So that means all the copper lattice, copper compact lattice it is called as, the atomic lattice on top of the gold 111 surface, and that copper lattice is basically all the lattices are rotated by 60 degree with respect to each other. So now when the cobalt is being deposited on the copper 111 surface, you directly see the symmetry of the surface is implemented in the island that is actually forming on top of the surface. That is very interesting. At the same time, you also keep in mind that cobalt is basically forming normally an HCP type of packing. Therefore, the symmetry of cobalt itself is also kind of 3-fold in nature, and that is the reason why you eventually see that the islands are actually forming in two different shapes like this, either a triangle which is looking facing like this, or a triangle that is basically looking like that. So one is actually called as a faulted half and the other is actually known as the unfaulted half, because on the copper 111 surface, when atoms start to pack, it can either pack all on the HCP side or on the FCC side. We will actually just give you some of the assignments here to just to grow materials on different type of materials. So there you can basically start to understand this in more detail, and then you can actually just see from the symmetry of the island formed itself what is basically going on at the interface. Good. Then any combination of materials may be used. So that is also the interesting thing about physical vapor deposition, that you can just evaporate any metal on top of any material. Yeah. So that is the idea. Now come to the chemical vapor deposition. So in the chemical vapor deposition, it's actually working in a way, in a slightly different way than the physical vapor deposition, because there is some chemistry going on here. So there are impurities, for the chances of having impurities are much higher in this case, and also like byproducts can be present in this case, and so on. So therefore, the preparation or the material that is actually prepared using chemical vapor deposition is not necessarily as clean as the one which is actually prepared by physical vapor deposition, but nonetheless the practices are much more optimized nowadays, and therefore people actually can prepare a very well ordered art layers of different type of materials on each other using chemical vapor deposition. Here the chemical vapor deposition is also very interesting because of the efficiency of the process. Yeah, it is actually a process through which you can actually produce much high quantity of thin films compared to a general physical vapor deposition. So how does it work? In every case of chemical vapor deposition, I will show you a couple of examples. What I want to do here in this case is I want to generate a polycrystalline silicon. I want to generate a deposition of polycrystalline silicon on any given surface. That is my task. So what I need to think about is I need to have a molecule that is having silicon as one of the ingredient. As you see here, if I would take trichlorosilane or silane itself, you can see that I have silicon as one of the ingredient. So that is the most important thing. Now you take these precursor molecules and mix it with some carrier gas, and then let these molecules with the carrier gas to travel onto a surface at which the reaction actually happens. What is the reaction? It is normally done with the help of temperature. Yeah. So you deposit the material, and while you deposit the material, you basically just do some kind of heating, and the heating would cause the silane or the trichlorosilane to basically dissociate, and then you can see atomic silicon is basically produced. Now the interesting thing here, in both cases the byproduct are gas molecules. That is the interesting thing. So the carrier gas that actually brought the precursor molecule will actually carry the byproduct away, and then finally the silicon is getting deposited on the surface. Well, I take a little bit, I make you understand this by taking a few examples. If I want to generate, for example, a silicon nitride layer, that is something quite important in technology. So there what I need is again silane, but I also need now nitrogen, because in the final product I want to have silicon and nitrogen. So I want to have a precursor of silicon, I want to have a precursor of nitrogen. So I use silane and ammonia, and basically this will be carried by a carrier gas and getting deposited at a hot surface, and then you form the silicon nitride, and hydrogen molecules are actually evaporated or removed, and this is basically carried by the carrier gas itself. So then you have another example. For example, I want to deposit tungsten. Yeah, here I just want to deposit pure tungsten on top of any surface. So again I need to have a precursor, hexafluoride I can take with tungsten as an ingredient inside. Again you can see the reaction is very simple. You take the tungsten hexafluoride and let it pass onto the surface where you want to deposit, heat the surface, and then you can actually eliminate fluorine. You can also take another mixture where you do a little bit of chemistry. In a sense, you take actually the hexafluoride, tungsten hexafluoride and hydrogen, you mix it, and then you basically just remove the byproduct as hydrogen fluoride. More examples you can actually just look. So this is very important. Indium phosphide, it is basically a semiconducting material which is very much used in silicon industry or in semiconductor industry in general. You can actually see how the equation happens. You can basically just prepare again an indium phosphide layer. So what you always need to keep it in mind, if I want to deposit something, I want to have actually a molecule which is having that particular element as an ingredient. But then you actually just mix it with some liquid, then mix it with the carrier gas, let us send it to the surface. On a hot surface it basically reacts. So that is the way it works, and always the byproducts are are gas, therefore the chemical reaction is actually not yielding anything which is getting deposited onto the surface finally, which is not the real requirement. That is the important thing. So, when you choose the precursor molecules, you just make sure that the chemistry will finally lead to a byproduct which is a gas. Now, let us have a look at the typical setup you require for doing a chemical vapor deposition. Of course, what you see here is a very schematic representation, and of course variety of design would be available. But in general, what you need is something of this sort. Well, you have the inlets for the gas precursors, and then for the solid precursors, what you generally do is you mix them in a solvent, and then you make a solution, and then using a carrier gas you basically just bring them to the reaction site. And then now it actually just mixes with the gaseous precursor that are coming from here, and then finally you let them into the reaction chamber. Now in the reaction chamber, so typically the reaction chambers are also always under vacuum in order to basically create an inert atmosphere, and then also to remove the byproduct. And now the precursor molecules would come deposited on the surface, and then on the surface, which is kept at higher temperature, the reaction would occur. And of course you have to have a better control of the temperature and the pressure of the reaction chamber, which is quite crucial for controlling the quality of the epitaxial films that you make. And then by controlling the temperature and the pressure of the reaction chamber, you can basically form nice epitaxial layers on the surface. And this is a very generic scheme, and of course, as I told you, you can have variety of designs for the chemical vapor deposition. Now we will have a look at a particular example. This particular example is also a very important example. It is nothing but graphene. I just want to show you an example of the preparation of graphene on graphene. That is actually a kind of chemical vapor deposition technique to prepare graphene itself. So what do? We have actually the precursor molecule, which is actually nothing but ethylene, where you have CH2 double bond CH2. Now this of course is done, this particular example is of course done in ultra high vacuum chamber, but you can also do it in high vacuum chamber or in normal chambers just to get the efficiency higher. And then what you do is you basically bombard the CH2 onto a hot surface. So you keep the surface which is actually at about 1000 Kelvin, and when the molecules go and bombard on the surface, so then the carbon atoms are getting deposited on the surface and the hydrogen atoms are actually pumped away in the chamber. That is a very basic thing, because carbon is the ingredient for graphene, and now you have the graphene ingredient, and now the carbon atoms go around, and since it actually happens on a two-dimensional surface, a surface which is itself two-dimensional in nature, basically the carbon get connected in a two-dimensional fashion or in a planar geometry, and the planar geometry is very important because that is what yielding the graphene. Yeah, if carbon would react in a non-planar geometry, so then you might have actually just grown diamond, for example. But in this case the graphene is actually just formed, and we do it on a platinum 111 surface. So this is actually an example. You can also see the details of this preparation in this particular journal, Surface Science. I always recommend you to basically just go and read these journals to understand the technique and also the details of the paper in a much better way than what we discuss in the class, because in the class we are only just trying to give you a small emphasis and not at the greater details. So now you see I actually kept the surface at about 1070 Kelvin, and I deposit carbon from the precursor ethylene on top of the platinum 111 surface, and this is actually the STM image taken at a low resolution and a high resolution image. So what you see here is actually many small islands you can see around. Yeah, so that is not very clear, but if you zoom in into some of the region, then you can basically see nice beautiful patterns you can see on the surface. So this is actually platinum, so that is not the graphene, but this is actually the graphene. this is the graphene, and you see some kind of a hexagonal pattern inside. Now, of course, you can also see there is actually a post annealing. So, you deposit at 1070 Kelvin, and as soon as the carbon get deposited, you also do something like a post annealing. The post annealing is very important in order to rearrange the carbon atoms on the surface and then to form a very ordered patterns on the surface. And now what we can do, we can zoom into a small region there, and then you can see basically that there is a very well ordered pattern inside, and each of the small bright atoms that you see inside is nothing but the carbon atoms. And you can also see that these carbon atoms, if you put them together, it actually forms a nice hexagon, as you have actually just seen in the case of graphite. We have actually just seen this example there. I showed you the graphene should have a symmetry looking like a hexagon. Now, but what is also interesting, if you look inside, not all carbon atoms are actually looking similar. They are actually just kind of changing their intensity. For example, the carbon at this spot is actually looking not that bright, but the carbon atoms at this point is actually looking much more brighter than the carbon atoms at this. So, that is actually making some kind of a super lattice, as you see here, which is again another hexagon. That is actually a super lattice, and that is generally known as a moire pattern. A moire pattern is actually some kind of a super lattice that is forming between two different type of crystalline lattices, not necessarily lattices between any different kind of materials. You will see some example, but in this particular case it is actually between the platinum, which is a 111 surface, it is again a hexagonal lattice, and you have graphene, which also has a hexagonal lattice. Now, when these two hexagonal lattices go on top of each other, they actually form something called a super lattice. We would look into great details in the next class about why is this super lattice forming, or what can you learn basically from the super lattice, and generally it is known as a moire pattern. We will discuss that in greater detail. But believe me that in this region, the atoms, the carbon atoms not adsorbed at the same position as the carbon atoms at this region. So, the carbon atom in this region is actually adsorbed in a different position with respect to the platinum 111 surface compared to this position. So, that is the reason why you have this modulation of contrast, and it is not only just the contrast modulation, it is also just the topography is basically modulating, because the atoms are actually just adsorbing at a different places. But now you can see in general, using chemical vapor deposition, you can actually prepare very high quality materials, and the general mechanism known for the preparation of this graphene itself is the simple thermal breaking of the carbon and hydrogen bond. But generally you know that the carbon hydrogen bonds are extremely more energetic than just 1000 Kelvin. So, typically if you have this as the potential well, which represent, let us say, the potential energy and the distance between the C and H bond, then you can basically say that you can basically say that this is basically the depth of the potential well, or the amount of energy required to break a CH bond. But generally this process is actually mediated by climbing across the vibration of the molecule. That means CH bonds are actually getting excited as the temperature increases. So, that means the molecules are actually getting excited into different vibrational levels, and finally the molecule, the CH bonds get broken, and then you form the CC bond, and that is how the chemical reaction happens. So, in the next class we will look into the different aspects of the formation of different type of adsorbate layers on surfaces and so on. Thank you very much for your attentions, and meet you in the next class. Thank you very much.